Okay guys, before we start today's lesson, I just want to remind you of the homework that will be due when we see each other again on Monday, so that you're staying up on that. We have advanced related rates. Remember, that was 3 pages that you'll staple together. And then a separate assignment will be notes and approximating area under a curve. Those two stapled together. Separate assignments turn in on Monday. Okay, we're going to do note card 49. Yesterday, our last class, we did Riemann sums of equal width. This note card is Riemann sums of unequal width. Okay, so we still have our same conditions up here that we had on the last note card, in that f will be continuous and non-negative over the interval, and we're using Riemann sums to approximate that area. However, now we don't have the same width every time. So that formula that we used on the last note card, the delta x equals b minus a over n, will not really apply here, because we are going to be given either a graph or a table, and we will just partition, in other words, come up with the rectangles based on the data. So the widths may change every time. And because of that, we won't be able to pull out a greatest common factor width. We will probably have to do a base times height plus another base times height and so on throughout the problem. Other than that, same thing as before. Okay, let's look at number 1. Actually, both of these problems are based on a past calculator free response problem. The rate of fuel consumption in gallons per minute recorded during a plane flight is given by a twice differentiable function r of time t, where t is in minutes. Excuse me. I have a graph there. Notice that this graph, this is a rate. Okay. We have a rate of fuel consumption over time. And then we also have a table of values. So I'm going to work off the table of values, but we might just use the graph as a little bit of a visual here. Approximate the value of the total fuel consumption using a left Riemann sum with 5 subintervals indicated in the table above. So we would recognize this as Riemann sums because since this is a rate of fuel consumption, if I approximate the area under the curve, I will be finding the amount of fuel consumed. So we want to use a left Riemann sum with 5 subintervals indicated in the table. And what they mean by that is, if you notice here, we can have our first rectangle with a base of 0 to 30. Second rectangle will have a base of 10. Third will have a base of 10. Fourth will have a base of 20. And the fifth rectangle will also have a base of 20. So there are our 5 subintervals. Subintervals, or also you might see the word partitions, that just means number of rectangles. Okay? Or that refers to rectangles, and this being the number of them. So the area is approximately first rectangle, base of 30, times height of. Now we want a left Riemann sum. So remember the trick we learned on the last note card. If you turn this way, you can kind of get a better visual of this. That first rectangle has a base of 30, and I want the left edge function value. So I'm going to be using these left edge values, which means this one will not get used. Remember, on an LRAM, that last function value will not get used, and on an RRAM, it would have been the leftmost function value would have not been used. So I will have 30 times 20 plus second rectangle is 10 times 30 plus third rectangle is 10 times 40 plus 20 times 55, and finally a 20 times 65. There is my approximation. On a free response, you could totally leave this like this. If it was a multiple choice, or if I was asking you to simplify for a homework assignment, we could now say equals, because now I'm going to say what these values actually equal. I've already showed that this is approximation for the area under the curve, and now these values actually equal to blank. And if you do crunch those numbers, you will get 3,700. So this is, remember, an approximation of the amount of fuel that has been consumed. So this is an amount number, so we will say gallons, not gallons per minute, because it's no longer a rate number. This is an amount. That is an approximation of the amount of fuel that was consumed over that time period. Okay, now let's look at 2. Is this numerical approximation less than the value of the exact area? Explain your reasoning. This goes back to what we learned on the last note card about how increasing and decreasing functions are affected by Riemann sums. Okay? So as I look at this function, the r of t values, the rate values, are increasing all the way through this interval. So this is obviously not what the graph looks like, because this is the graph. However, this is just a reinforcement of what we learned on the last note card, and that is when you have an increasing function, that LRAM will be underneath the curve. And you could also use any partition here. You could look at, for example, 0 to 30. Maybe that first one, let's just look at that first rectangle here. 0 to 30, LRAM, so we're stopping the left edge first. And you notice that we are clearly have some space left over there that we didn't account for. So this is an underestimate. So we will say this is less than the actual area, and you could use also the word underestimate. So I'll say this is, I'll just use the wording they did. This is less than the exact value because R of t is increasing, therefore an LRAM produces or yields an underestimate. Now remember, you have a little bit of latitude in how you would choose to word this. That is certainly not word for word the only way you could say it. The key things that an AP reader would be looking for is that you've referred to R of t increasing, meaning an LRAM would produce an underestimate. So those would be the key things there. Less than the exact value for those reasons. Right? Okay, so that's note card 49, Riemann sums of unequal widths. Make sure everybody's had a chance to finish writing down those two problems. And now we're going to look at yet another way to approximate the area under a curve. We've only been looking at rectangles so far, both of equal width and unequal width. And now we're going to talk about how to use trapezoids instead. So trapezoids, we're going to still have some same conditions here, and that is that f must be continuous over a given interval, and we will have n subintervals of equal width. Now, we don't always have to have an equal width, so what I'm actually going to do is talk about how to do trapezoidal sums. And then when we're done, I'm going to come back and talk about how this trapezoid rule was formed, and I think it will make more sense to you at the end. You can actually handle all trapezoid problems without ever using this. However, if you do have equal widths, and you recognize how to set this formula up, it is simpler and can make a problem maybe a little bit quicker. But it certainly isn't something that's mandatory. You can always do a trapezoid problem by just doing one trapezoid at a time, similar to what we did on the last note card where we were having to do the area of each rectangle separately. That's the way we'll handle trapezoids. And then, like I said, at the end, we'll take a look at this rule. Okay? Okay. So we're going to use the trapezoidal rule or trapezoidal sums to approximate the integral from 0 to 2 of x cubed dx for n equals 4. So we want to have 4 trapezoids. So I'm going to find out what will be the height of each trapezoid, or I should say the base. And let's remember what we're talking about with the trapezoid here, okay? So let's just say we have something like this going on. I'm going to move to the board in just a second and do this a little bit larger. But a trapezoid is a figure where you have exactly one pair of parallel sides. So you may have something like this. This would be a trapezoid. More commonly, you guys are probably used to seeing trapezoids like this, which would be an isosceles trapezoid, where these legs are the same length. We're going to be using trapezoids that look more like this here. Okay? So as we see here, these trapezoids are going to be used to approximate an area under this curve. So I'm actually going to go up to the board now and get a larger graph of x cubed over the integral from 0 to 2. And I know this is actually a new symbol that you're not used to, and we're going to talk way more about this next week. But for now, I want you to just, when you see this, this is meaning the area under this graph from this x value to this x value. So the area under x cubed from 0 to 2, and we will dive more into this notation later. Okay? Okay, so I'm going to go to the board now, and we are going to graph x cubed from 0 to 2. So before I do this, remember our cubic parent function looks like this. But I'm only going to be interested in this part of it from 0 to 2. So I'm going to zoom in on quadrant 1, so to speak. So let's draw a nice big quadrant 1 here. Okay? And we're going to go 0 to 2. And what I want to do first here, I'm actually going to go back to the paper, sorry, just for 1 second, and we will find out what is going to be the width of each trapezoid? So we're going to use that same formula that we use for Riemann sums of equal width. We're going to say delta x equals b minus a over n. So this will be 2 minus 0, remember the x values, over the number of, in this case, trapezoids we want. That's 2/4, which is 1/2. So we want every little width of the trapezoid, which we're going to actually call that a different, we're not going to say width in just a second. We'll talk about what we're going to say about that. But we're going to have 1/2 be our distance on our partitions there, okay? So basically that means going from 0 to 2, counting by 1/2. That's what's happening. So now I'll come back up here and we're going to start at 0 and we're going to go to 2, counting by 1/2. So let me make a nice large graph here. So 1/2, 1, 1.5, 2. So there we go right there. And now, talk about these function values here. Well, the largest value is 2, and 2 cubed is 8. So I need to be able to get up to 8 on here. So I'm going to let the tick marks be a little bit closer together on the y-axis here so that I can get up to 8. I think I've done that there. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, we're good there. You can number them all if you want, or whatever, however many you want to number there. Okay, so let's put in some values now so we can get a look at this graph. When x is 0, y is 0. Of course, the cubic function goes through the origin. We know that, the cubic parent function. When x is 1/2, we're going to have 1/2 cubed, which is 1/8. So that's not very far up there. So let's do some of these other values here. We'll just get a nice look at this. When x is 1, 1 cubed is 1. And when x is 2, 2 cubed is 8. So the other values will kind of take care of themselves in a second, but we just wanted to get kind of a zoomed in look at that cubic function from 0 to 2. And now we're going to have trapezoids. And every trapezoid will be partitioned by 1/2 here. So, but notice the first trapezoid does not even have a distance for this leg. So it really is a what? Triangle, hopefully someone is saying. And now, trapezoid 2. This actually is a trapezoid. I have a 4-sided figure there, don't I? 1, 2, 3, 4. And now this would be 3 halves. We're going to go up to here. Remember, there's no LRAM or RRAM. You're letting each leg go till it hits the graph because we've got to have both sides there for that trapezoid. And now we're going to go up here till this guy hits. And obviously he's going to hit at 8. I got a little off there because I'm not using grid paper. And that's a little bit off of, pretty much you can see that. So hopefully you can also see that this is going to be a little bit of an overestimate, but not as bad of an overestimate as we get with Riemann sums. And we'll talk about why that produced an overestimate in just a little bit. Okay, okay, so let's go ahead and do this. And remember, this notation is simply talking about the area under the curve from 0 to 2 for this function. The rest of this is like, we're going to talk about it later, so don't get freaked out by that right now. Okay? And once again, I shouldn't say equals, I'm going to say is approximately. Okay? And now we're going to work this out here. So I'm going to take each trapezoid one at a time. Now we need to remember our formula for the area of a trapezoid. Okay? Just keep this up here to make it easier. Okay? So we've got the area of a trapezoid is one that if you don't have memorized, you will re-memorize it very quickly here because we're going to use it a lot. The area of a trapezoid is 1/2 the height times the sum of the bases. Now, this first one's a triangle though. So this is just 1/2 base times height. The triangle formula actually comes off of this, but one base is 0. So if one base is 0, then look what I have, 1/2 base times height. So the triangle formula is just a application there of the trapezoid formula. So I will have 1/2, that is this distance right here, okay? 1/2 base times height. Now, we've got obviously a base of 1/2. I said the formula already has a 1/2 in it. And now I've got this 1/2 here. Because, tell you what, let me go ahead and mark these off. This may help us. Okay? So this triangle will be 1/2, base of 1/2 times height of, we need the function value for that height. I need f of 1/2. 1/2 cubed ends up being 1/8. So there will be my first figure. That will be the area of this triangle. Now the rest of these will actually be trapezoids, okay? So I'm going to have 1/2, and then another 1/2, right? Because this still is a distance of 1/2 there, okay? And this will be f of 1, which we know is 1. So 1/2 the height times the sum of the bases. So this was 1/8 and this was 1. So base 1 and base 2. So 1/2 the height times the sum of the bases. So notice we're using this base again. We used the 1/8 here for the triangle, and now we're using the 1/8 as part of this. And you're going to notice that pattern continuing. All of these legs will get used more than once, except for a couple of them. And that will kind of take us back to the top of the note card where we can see where that rule came from. Okay, third trapezoid. I've got 1/2 the height. Notice this is always 1/2 times 1/2 times the sum of the bases. The third trapezoid will have a leg of 1, and this one will be f of 3/2. So we'll need 3/2 cubed. Well, let's do a little arithmetic here. 3/2 cubed means 3 cubed over 2 cubed. 3 cubed, that's a 3 here, sorry. 3 cubed is 27 and 2 cubed is 8. So we have 27 over 8. And now we're to our last trapezoid. 1/2 the height times the sum of these bases. We're going to use the 27 over 8 again. And we're going to use this edge, which is f of 2. And 2 cubed is 8. And there we go. Okay, once again, that is an approximation. You can leave this like this, or you can simplify it further, okay? So if you do simplify this further, this was our triangle, and then these were each of those trapezoids, weren't they? Okay? So if you go through some arithmetic and simplify this further, you would end up getting 4 1/4, or 4.25, okay? And I'll leave all that arithmetic to you. But once again, on a free response, that would be a terrible idea. You want to leave it like this. On a multiple choice, if they made you go to this place, then you would need to do that. Otherwise, you wouldn't have to. But if you do go through your fraction work and through a little arithmetic there, that's what you get. Okay? You would get 4 1/4 or 17/4 as an improper fraction. Or, of course, you could also write that as 4.25. Either way. Okay? Now, before we go on, I want to kind of link what we just did to this trapezoid rule up here and see if it starts to make a little sense to you. Okay? The trapezoid rule says that this process that we just did, as long as we have the same partitions here, okay? And I want you to think about what was going on here. This that we used to call the width of the rectangles is actually now the height of the trapezoid. Let me just do a little pull out on this trapezoid here and flip it this way. And this trapezoid would look like this. I've just taken this guy and done this. Okay, so here's that height. And these were the bases, B1 and B2. So as you look at these problems, this now actually is our H values for trapezoids. Whatever this distance is, which in this case was 1/2 every time, that's going in for H. And these values here, the length of these legs, those are going in for B1 and B2. Okay? So sometimes turning it this way kind of gives you a little idea of that, but we're going to always see them in this fashion here. All right, now, how does what we did link to this up here? Well, if I cover up this, sorry, I'm going to move back over here now. B minus A over N looks familiar to us because B minus A over N is how we find the delta X for our Riemann sums. Now this says B minus A over 2N. Let's think about what that must be. What was B minus A over N for this problem? It was 1/2. And doesn't the trapezoid formula already have a 1/2 in it? So this H was found, I'm going to erase this little arithmetic we did here. This H was found by doing B minus A over N. It just happened to be 1/2 for this problem. But this was B minus A over N. We got a 1/2. If you times it by the 1/2 that is already present in the trapezoid formula, you would get 1/4, or better yet, think of it this way. This formula times this 1/2, 1 times B minus A is B minus A, and 2 times N is 2N. That's where this comes from. So this is simply a combination of your height of each trapezoid, assuming they are the same heights. If they're not the same height, this rule is useless. If the trapezoids are not the same height, like the Riemann sums of unequal width on the last note card, if the trapezoids are not the same height, you've got to do it this way every time, one trapezoid at a time. But if they are the same height, you can use this formula, because B minus A over N gives you the height, you times it by the 1/2 already in the formula, and you get this. So that's where that part came from. Now, the rest of this looks like it's saying that we use the first function value once, we use all these other function values twice, and then we use the last one only once again. That's what it's saying. And that makes sense because look what happened here. And I didn't write a 0 here for this because we just used the triangle formula. Had I wanted to strictly use the trapezoid formula here, I could have still said b1 plus b2, but the first base would have been 0. So look what happened here. I used the first base only once, and I used this last base right here, the length of 8, I only used that once. Every other base got used twice. Look at this. Every other base got used twice. The 1/8 got used twice, the 1s got used twice, and the 27/8 got used twice. That's what this formula is telling you. Use the first function value once, the last one once, and all others twice. So this is just a little bit of a simplified version, or maybe a shortcut for what we did. But it can only be used if your trapezoids are of equal heights. Otherwise, it's useless. Okay, so now let's look at number 2. The function f is continuous on the interval from 2 to 8 and has values that are given in the table below. Using the subintervals 2 to 5 and 5 to 7 and 7 to 8, what is the trapezoidal approximation of this? And we're just reading this today as the area under this graph from 2 to 8. So let's go through this and set this up. And we'll say, we'll just rewrite this notation, which we're not very familiar with yet, but we know to put a little approximation squiggly equal sign there. Okay? Okay, so I don't have the same widths. I have, or I should say the heights of each trapezoid. That trapezoid will have a height of 3. This one will have a height of 2, and this one will have a height of only 1. So the trapezoid rule is useless here. I got to do one trapezoid at a time. So trapezoid number 1 here will be 1/2 the height. Remember, the height is the distance in the x values, like we saw here. The distance in the x values is the height of the trapezoid. So from 2 to 5, that's a 3. So 1/2 the height times the sum of the bases, which is 10 plus 30. That is trapezoid 1. You don't have to, I mean, on the note card I would like you to do this, but on an assignment you wouldn't have to do, say, trap 1 there. We're just doing this for a learning tool. Trapezoid 2 now. 1/2 height, 2, times the sum of the bases, and that's 30 plus 40, and that is trapezoid 2. And finally, trapezoid 3. 1/2 height of 1 times the sum of the bases, which are 40 plus 20. Let me move this up just a little bit here. Right. And that is trapezoid 3. And now I'm going to say equals. Let's say if this was a multiple choice or maybe a homework assignment where I ask you to simplify, this would be 40. What I would probably do to avoid fractions is to say 40, half of 40 is 20, and then times by 3. So I get an area of 60 there. Let's use the same technique here, okay? This would be, well, this is really easy because half of 2 is 1. So that goes away. We just have 30 plus 40, which is 70. And third trapezoid, I have 60. Half of 60 is 30, and 30 times 1 is still 30. So I have 60 plus 70 plus 30. I have an approximation of the area under the curve as 160. Okay, now, before we leave this note card and are done with this lesson, I want to talk about when will trapezoidal sums yield overestimates or underestimates. We've already linked Riemann sums to increasing and decreasing. We know how increasing or decreasing functions will determine whether LRAMs or RRAMs are over or under estimates. What is the connection with trapezoids? Well, let's just take a look at a little bit of a version of what we just did here. It looks like the problem we just did on the board a second ago yielded a slight overestimate. Is that because the function was increasing, like the connection with Riemann sums? Well, let's see. Let me do a decreasing function. But look, the trapezoidal sum there is still an overestimate. So it doesn't look like increasing or decreasing is what's going on here. What is in common about these two curves? Hopefully, someone is saying that they are both concave up. Let's look at concave down. And once again, I'll look at concave down decreasing, and I'll also look at a concave down increasing. And look what's happened here. slight underestimate. And if I widen out my trapezoid, it's more dramatic to really see that. So trapezoidal over or underestimates are not linked to increasing, decreasing, but are linked to concavity. So on the back of your note card, let's see if we can summarize this. And I'll just use f of x for the function. And I'm going to abbreviate here to make it easier on everybody because we know what CU and CD mean. That means concave up. So if f of x is concave up, trapezoidal sum is an, we just saw concave up is yielding overestimates, isn't it? Concave up, overestimate. And finally, if f of x is concave down, then the trapezoidal sum is an underestimate. And that is the conclusion of this lesson. So let me leave you with our homework assignment, because I know you would want to not have, you wouldn't want me to forget to do that, I'm sure. So we've got 2 pages for homework. We've got calculus worksheet on Riemann sums and trapezoidal rule. This should be right after the trapezoid note card that we just did. And then this is chapter 4, multiple choice after related rates. You're actually going to have to go back to find this. This is before the note cards that we did today. So you'll want to flip back a few pages and you should find that. So that is your homework over the weekend. And that will be due when we see each other again on Monday. Have a nice weekend.